Right, the final part of our lesson is to talk about stress concentrations. So what are stress concentrations? So I want you to consider this member, right? We have drawn roughly uniform blocks on the member, but we have this hole in the center of the member. When I pull on this, when I apply a stress, a uniform stress to both ends, how is this member going to deform? I'll go ahead and pull on it, and hopefully you can see it in the video. You should see that it deforms, and through much of the member it stretches out, but particularly around the hole, we see that the hole gets to be more like an oval, and that it's kind of, the stress pattern around the hole is a little bit different than maybe away from the hole in the cross-section of the member over here. All right, so I want you to think about that stress pattern as we're going to go ahead and sketch it here in our notes and talk about the stresses occurring at different sections.
Well, I'm going to do my best to sketch that deflected shape. So under the load P, we know the bar will extend to the right. We also saw from the demonstration that the circular hole in the middle kind of became an oval, and we saw that the plate sort of drew in closer to the circular hole at the center. So if we imagine one of these blue lines along the length, as it gets closer to the hole, it kind of got bent around the hole, and we saw it kind of deform. And so hopefully this is something close to the pattern that we saw in the demonstration. It's not my finest artwork, that's for sure. So also to note, away from the hole, we do have some uniform extension of all of these blocks. So these blocks are slightly larger than the blocks in the figure above, where we have just the load is just starting to be applied. I want to take a look now at the stresses that are occurring at section A through the hole.
We see that the average stress in the member is going to be highest around the bolt hole because that is where we have the least amount of material to resist the applied force. And I think if I showed this to you and I said I was going to pull on it, where do you expect it to break? I think you would come to the conclusion it should break something like that, right? Right at the top of the circle. Okay, so we know that it has the highest stress there because it has the smallest section, and we need to come up with an expression for that average stress at the section. Now remember that average stress at the section does not include this bolt hole, so we have to come up with an average stress for just this top and bottom segment. So let's come up with that formula now.
Coming up with the average stress formula is no more than just paying attention to the geometry of our section. So I'm going to shade in here the area of the member in question. So remember that when the bar fractured, it separated above and below the bolt hole. And so our area, the area that's connected, is less than we had originally with the bar because we have to account for the reduction due to that bolt hole. When we look at average stress, we assume that the stress is the same everywhere across this area. And average stress is what we've so far have dealt with in mechanics of materials. We always take the load P divided by the total area, assuming that the stress is uniform across the entire member. And so a uniform stress looks something like this. I try to draw it here in 3 dimensions, and I kind of just will shade this in so that we see that it's kind of like a uniform stress block almost that's extending away from the material. To come up with an expression for average stress, we just use our formula P divided by A. Again, we just have to calculate a different area that accounts for the loss of the whole. So our average stress will be P divided by, and now we have to come up with an expression for this area. So I'll go ahead and highlight this area over here. This is the area that we wish to find. Now, the area is the width times the thickness of the member. So that's the total area. But remember, from that width times thickness, we drilled out a hole. And so we have to lose an amount, and the amount that's lost is equal to the diameter of the hole times the thickness. And in this case, I'll call the diameter 2 times the radius. And this will just help us with our future plots and graphs that we're going to need. It always refers back to 2 times the radius, which is equal to the diameter. So rewriting my area, I can say that my area is the width minus the diameter, and that quantity times the thickness. And so there I come up with my expression for sigma average.
All right, so we now have an expression for what the average stress at this net section is. But is that the actual stress that's happening in the member? Well, to analyze the stress that's happening in the member, I like to I'm a little crazy, and I think of stress as like little people that are marching. So think of like a marching band, right? You know, they're very spaced out, very uniform, and that's how stress likes to travel through a member. So stress likes to be spread out and uniform. So in our particular example, the stress over here is spread out and uniform, and everything's going okay. But then as you approach the hole, the stress has to somehow make its way around the hole. And so what will happen is that if you can imagine somebody marching here, you know, they have to kind of either go up and around or down and around, and things will bunch up, and we'll actually see what we call a stress concentration. So we'll see that the stress at this point in the circle is going to be higher than the stress outside here on the plate, because the stress is kind of bunching up. Now I have a little demonstration that I like to do, and so I need you to imagine a crowd of people, right? So and when we're in the classroom, I can get you guys all involved, but I don't have you guys here today, and so I need you to imagine a crowd of people, right? And they're marching or walking, you know, down a pathway. And suddenly, there's a silly trash can in the middle. So what happens is all these people are making their way, and there's like a trash can in the middle of like the hallway or something. So as you approach and you walk, people that are far, like off to the side of the trash can, they're going to walk along and they're going to be okay. You know, they might feel a little bit more crowded as they pass, but they're not going to feel super cramped. But people that are walking and are approaching the trash can head on, they're going to have to start to go around, and then they're going to be like squeezed in, and they're going to start jostling shoulders with everybody else. And so that's kind of my interpretation of stress. Stress will be bunched up right here at the edges of the hole. So the trash can represents the hole in our member. Stress will be bunched up here on the edge, but as you kind of get removed from that edge of the circle and towards the edge of the plate, you are less bunched up. So that's kind of the idea with stress concentrations. We can apply this concept to a variety of cases, as we'll see. So go ahead, just think of my little stress people when you're trying to do a stress analysis for engineering.
A stress concentration is a point in the member where the actual stress is higher than the average stress at that section. So from our demonstration, we observed that stress will not be uniform or average across this particular section, but that stress will tend to bunch up along the inside circle, right where we have that hole, and then away from the center hole towards the edge of the plate, the stress will be reduced. And it'll actually, in this case, be like a parabolic drop-off to the edge. So this is going to represent our actual stress, much higher right at the hole location on the edge of the hole, and then lower as we get towards the edge of the plate. So while the average stress will remain the same, the maximum stress causes a little bit of a problem, because if material fails, it starts to yield or it starts to fracture whenever the stress exceeds that value at a particular point. So we have to be concerned with coming up with this maximum stress in a case such as this. Now, we could come up with the maximum stress by looking at some forces in the x direction. So some force in the x would give us P minus sigma A, where sigma is a function across the area, equals 0. And then we could take P and solving for the load P, we would then say that it is the integral over the area of sigma dA. Now, this is great if you like to do calculus all the time, but if you're not really game for that, or if you don't have time to do that and you're a busy engineer, we often have some tabulated values for stress concentration factors. So we need to come up with sigma max. So sigma max is just some factor times sigma average. So we call the stress concentration factor capital K. So solving for capital K, we can write an expression that capital K equals the maximum stress divided by the average stress. And again, if we're concerned about failure, we need to make sure that our maximum stresses fall below certain limitations so that we don't have premature failure at the inside edge of that circle.
So we can apply this concept of stress people to even more complex cases. So as part of my PhD research, I did some research on angle members. So an angle member has an L cross-section like this. And these are often used for braces, cross frames in steel bridges. So these angle members get attached to a flat plate. And so, and they're typically welded to that plate. So I've drawn in the blue line here to represent that weld. Now, away from the connection, the stress is uniform. So I've kind of put these red tick marks in here to indicate that the stress is uniform at this point. So again, imagine my marching people. They're marching and they're uniformly spread out across all the cross-sectional area. However, as we get to the weld, you got to think like the weld is like the exit doors. So imagine this is the hallway, but this blue line represents the exit to the building, and all these people are trying to get out. So as the stress approaches the connection, you'll see that as soon as there's an exit, right, that stress wants to leave. And then this next one will also try to leave. And this one will also try to leave. And so we'll see that a bunch are trying to leave right here at the forward edge of the connection. So we'll actually develop a stress concentration at this location. Now, the stress will continue to spread out. Now I want to consider the stress up here, right? Well, the only exits are what's attached to the plate down here at the bottom. So these stress people need to make their way down to the exit somehow. So maybe this one is really going a little bit further along the length. And these start to exit. Some of these start to transfer into the bottom hallway. And we'll see that in addition to a stress concentration here, some of this stress, because a lot of this stress is accumulating down here in this portion of the hallway, will develop a little bit of a stress concentration down here at the back edge. we'll also maybe see a little bit of a rise here. But the highest stress concentration is typically here at the forward edge and then here at the back edge. So hopefully that helps you kind of see a more complex application of how do we figure out the stress distribution. Now, how do we come up with the stress concentration factor? That's going to be exceptionally difficult. For simple cases, we have them tabulated, but for a complex case like this, we're going to have to run a series of analyses. And so what you see next in the notes is actually what we call a finite element analysis of this connection. Now, don't be scared by that terminology. It's really everything that you already know how to do. In a finite element analysis, we are simply applying equilibrium, kinematics, and material law over and over and over again for a large, for an object. And basically, instead of getting maybe like 2 equations and 2 unknowns, you're gonna have to keep doing that process to get, hundreds or thousands of equations and thousands of unknowns, and then the computer will help solve it down for you. And so that's kind of the only difference between that complex analysis and what we've been doing in class is that it just requires more application of the same equations, material law and kinematics, over and over again to develop those relationships as well as equilibrium. All right, so go ahead and finish completing your notes. I'll get back to you on an example problem.
This is an example of what output you would get from a finite element program. So it takes all the forces that you apply and all the connections. It runs, equilibrium, kinematics, and material law over and over again, and then will report back the stresses at different locations throughout the member. We see that we get a hot spot stress right at the forward edge of the angle. We also get it at the back edge of the angle, but the hot spot stress there occurs in the connection plate. This is useful for complex geometries, and it allows us to come up with a stress concentration factor by taking the hot spot stress and dividing it by the average stress. While we can always do a hotspot stress analysis, it's sometimes not practical, especially for well-known cases. So the case that we've studied so far, a plate with a hole in the center, that's a pretty standard and well-known case. So for these cases, for commonly encountered geometries, we have tabulated the stress concentration factor values based on the geometry of the plate and the geometry of the hole. So in order to determine the stress concentration factor, we would come in and we would look at the diameter over the width, so that's 2r over w, obtain that ratio, start on the x-axis, move up to the curve, find where we intersect the curve, and then move to the y-axis. Wherever we are on the y-axis, this is then our value for the stress concentration factor, K. For some of the geometrical properties and the average stress, you can look in the little inset and you'll see all of the geometry and the average stress formula defined.
All right, so now we have a basic understanding for a complex case, but in engineering mechanics class, we're just going to stick to some of the basic cases. So we'll stick to this case with a plate with a hole in the middle. The other case we'll look at is a plate that has fillets in it so that it reduces to a smaller cross section. So again, we want to consider that this has a stress concentration. So I think of if you kind of imagine you're walking down a large hallway and you have doors at the end of the hallway to get out. As you start to approach, the people from the edges are going to start cramming and pushing to get in, and a stress concentration will build on the inside of this radius, inside radius of this fillet. So, and the critical point will be in the smaller cross section because that's where the people will be most bunched together, and not only in the smaller section, but they'll be most bunched together on the end. So if we pull on this, you would hopefully, unsurprisingly, expect, there we go, unsurprisingly expect that failure would occur right where that transition of that fillet radius begins. on the smaller section. All right, so these are the two types that we'll consider for stress concentration factors. So we'll go ahead, you can take a look at the stress distribution for this, the average stress and the actual stress, and the plot, and then we'll do an example problem.
Well, I hope stress concentration factors are making some sense to you. Again, a stress concentration is just somewhere in the member where the actual stress is higher than the average stress. And we just need to be aware of these stress concentrations when we design so that we don't accidentally exceed the yield or ultimate stress at one particular point in the cross-section. That could cause problems with our design, again on a case-by-case basis depending upon the requirements of your part. For a bar that is transitioning from a smaller section to a wider section with these fillets, the stress concentration plot is given here. This will require two geometrical properties, the radius over the value h as well as the width over the value h, in order to determine the value for the stress concentration factor K. And we'll see how to utilize this plot in our example. Again, I remind you that that insert will define all of those geometrical values as well as the average stress we need to use in conjunction with the stress concentration factor.